In this short video, we're just going to talk about the material that's part of the lab and the assignment of the day for the refrigeration theory tab of your core refrigeration course. Okay, I'm going to start off with this assignment of the day because this is the electrical part of it. The rest of it has to do more with refrigerant pressures and other stuff like that. So let's go ahead and get the schematic out of the day first. What you are being asked to do is draw a ladder schematic of 3 light bulbs in series, controlled by a single switch with a second single pole switch that bypasses one of the bulbs. Okay, so what we have is a bypass circuit, and they are used occasionally in HVAC for various safeties, as well as for electric heat and other things like that. So it's worthwhile taking a look at this. So series start off means one path for current to flow. So let me switch over here to my whiteboard. And again, as usual, excuse my lack of straight lines because I am sometimes not the best whiteboard drawer. And what we're going to do is we're going to go ahead here, okay, and we're going to start off with line. Might as well put our neutral in here as well, because those are going to be our 2 points. So we come out of line. We have to have a single pole switch that controls everything. Okay, then I'm going to have 3 light bulbs in series. Bulb 1, bulb 2, bulb 3. Again, single path for current to flow. We come back to neutral. Okay, now it says I also have a single pole switch that bypasses or controls one of the bulbs. So we'll put a switch in here in parallel with one of the bulbs. Okay, so we have our service switch. We have our SW1. We have our B1, B2, B3. Now how this actually works, okay, is that my single pole switch, okay, is open. So it forces the current flow to go through all 3 bulbs. It has no choice. Now, if I close this single pole switch, okay, and of course, when this is going on, we do have service switch closed. If I close the single pole switch, my current or flow of electricity is going to take the path of least resistance. B3 has resistance. A switch in a closed position doesn't. So instead of going through here, okay, my current flow is going to come through this way and bypass that last bulb. So if we switch back over to what our assignment is, draw a ladder schematic of 3 light bulbs. We have my 3 light bulbs, okay, controlled by a single pole switch with the second single pole switch that bypasses one of the bulbs. That's what our drawing here is, okay? 3 light bulbs controlled by a single pole switch with a second switch that bypasses one of the bulbs. Wire it and give it a try. Okay, so that takes care of our assignment. So let's go ahead and take a look at the lab projects that are here. Let's go ahead and start with Lab 3A. It's a good place to start. Okay, upon completion of this exercise, you'll be able to read a temperature pressure chart. Well, then it gives you a bunch of numbers and temperatures to convert to pressures with refrigerants. Okay, so I'm not going to do all of these for you, but what I do want to do is take a quick look at a pressure chart, and we're going to take a look at that R22 at 55 degrees. So what I'm going to do is I want to take a look at this one right here. Okay, and we're going to go ahead and convert that one and that temperature to pressure. So if we go over here to my pressure chart, okay, we need to find the top of the column where we have R22. Now, every pressure chart is a little bit different based on different manufacturers. Okay, so what we need to do is find R22. R22 most often is this green color. Okay, so my temperatures are down the left-hand side of this chart. My pressures are all in the column under the refrigerant. So our temperature is 55 degrees. It's right there. Let me get rid of some of this line. Okay. So what we do is we come down the 22 chart to the pressure that's to the right of the temperature, okay, where the two lines intersect. Okay. So we have, again, I have my temperature of 55 degrees, my R22 column, and my pressure that intersects the two. So the pressure of R22 at 55 degrees is 92.6. So my answer to this one right here, okay, would be 92.6. Now, let's go the other way, okay? In this case, we have, again, R22. Okay, we're going to look at this one. We're going to look at my R22 at 68 psi. So coming back over to my temperature pressure chart, let's get rid of what I just marked up the first time, okay? Nice thing about a screen eraser. Okay, but what I am now looking for is I want to find R22 at 68 psi. My closest is going to be 68.5. Okay, come to what your closest number is. Okay, come over to the left-hand side. My temperature's 40, or slightly under 40. It's probably going to be like 39 or something like that, but 40 is close enough. Okay, so we know R22 at 68 psi is going to be right at 40 degrees. So my answer over here is going to be 40 degrees. And you might as well put an F on it because we do want to let people know it's Fahrenheit. Okay. So we can do this with any one of our combinations. Okay, so again, let's take a look at R134A at 94. So come back over to my temperature pressure chart. Let's find R134A. Okay. There it is. It's the baby blue or sky blue color. Okay, so my temperature I'm looking for is 94 degrees. So we come down the left-hand column. See, now we don't have 94, but it's very close to 95. Okay. My column here, we're going to come down my R134A column and find the number that's closest to. So it's going to be right around 114, 113. I'm going to go under in my answer, and I'm going to say it's going to be 113, that area. Okay, so my answer over here would be 113. Okay. Now, again, we can do it the other way around, and let's find R134A at 2 psi. So let me just go and erase this little line that I put in here so we don't get all confused. So I'm going to come to R134A at 2 psi, which 1.9 is my closest. Oh, by the way, the reds are vacuum, okay, and negatives. So this would be like inches of mercury vacuum. So 1.9 in the black, which is my positive. Come over to my left. Okay, it's negative 10 degrees. So 134A at 1.9 or 2 psi is negative 10 degrees. So we can come in here and we can do the same thing. Let's make sure we get the negative sign on there. Okay. And we mark that negative 10 degrees. So that's how the temperature pressure chart works. We have a couple questions in here. What's the purpose on the fins of the indoor and outdoor coil? Honestly, it's to increase the surface area. The more surface area of metal the air blows across, the better efficiency you're going to get out of an evaporator or condenser coil. Okay. The interconnecting lines is the largest. Suction or liquid, it's going to be my suction line. Liquid line is your warm line. That's warm liquid. okay, coming from the condenser to the metering device. The suction is my larger line. It's a vapor line, and it goes from the evaporator back to the compressor. The state of the refrigerant as it leaves the metering device is a flash gas. It's basically a mixture of a very little bit of vapor and a lot of liquid. It's almost like a spray out of the end of the garden hose. Latent heat. Latent heat is the heat that's required for the change of state. Okay, sensible heat is the other type of heat. I can measure sensible heat. It's the heat you feel in a room. Latent heat you cannot measure, but it's the BTUs required to be added or removed to a substance when we change its state. For example, if I melt ice from a solid to a liquid, I have to add heat. Okay, I can have 32-degree ice, I can have 32-degree liquid. It's the same temperature, but one's a liquid and one's a solid. The difference between the two is the latent heat. Same thing happens in a refrigeration cycle from liquid to vapor. I can have 60-degree liquid, I can have 60-degree vapor. The difference is the amount of BTUs that have been added or removed to do the change of state. The main parts or components located on a low pressure side is the evaporator. And if you want to talk about line sets, it's going to be your suction line. The main parts of components located on the high pressure side, it's going to be your discharge line, your condenser, and your liquid line. I'm not including the compressor or the metering device because those are my 2 points of pressure change in the system. What determines the temperature at which a refrigerant will vaporize or boil off? It's the pressures. When we looked at the temperature pressure chart right here, this is telling you at what temperature my boiling point will occur because of the pressures. Temperature pressure chart. Okay. What type of heat is removed in the condenser? Well, we have our sensible heat. We have to get the temperature of the refrigerant down to the level it will condense. And then we have the latent heat that's removed to condense the refrigerant from a vapor to a liquid. And then we have some more sensible heat to do the desuperheating. The purpose of the compressor is to compress the refrigerant and raise its pressure. Raising the pressure in tune raises the boiling point so that the refrigerant boiling point is over the ambient air temperature. So heat will naturally move from the condenser, from the refrigerant inside the condenser, to the air blowing across it. What component absorbs heat? It's my evaporator. We absorb heat in order to boil off the refrigerant. What component rejects heat? It's my condenser. My condenser pushes heat from the refrigerant to the air around it or blowing across it. So that is basically Lab 3A. Okay, it's all about temperatures, pressures, and the different components in the refrigeration system. Lab 3B, okay, upon completion of this exercise, you'll be able to locate the temperature glide on hotshot refrigerant, which is a drop-in replacement for R12. Okay, hotshot is a blend. Okay, what we're asking you to do is go to the web, do a web search on hotshot refrigerant, find a temperature pressure chart, and then do the same thing we just did. Okay, you're going to find the temperature find the temperature for pressure for 130 pounds on the high side, record it. Find the temperature pressure for 32 pounds on the low side, record it below. What is temperature glide? Okay. Temperature glide is basically a range of boiling points at a specific temperature in a blended refrigerant. When I mix multiple types of refrigerants together, okay, I may have more than one boiling point. Temperature glide is that range of boiling points at a certain pressure. Looking at a chart you found on the web, do you see a temperature glide? You very well should. Okay, how would the website be helpful to you in the field? Well, I can think of a number of things, okay, because it provides the technical support for the refrigerant. Okay, you might need it to find the correct refrigerant. You might need it to see if you have a leak. You might need it for troubleshooting. Okay, there's no drawings on this lab. But again, be able to use your web resources for technical support. And that wraps up this short lesson on or overview or recap of what's in your lab 3A and 3B. Actually, let's take a 3C real quick. Temperature conversions. Okay, just has you doing temperature conversions from Fahrenheit to Celsius. It's multiplication and division. Okay, take some time and go ahead and do these. It's calculator, and they're relatively easy.